So, good morning. Welcome to Krishna's classes. Today, we explore two major properties of the Lebesgue machine. Just recall, we have already defined what Lebesgue measurable sets are and what a Lebesgue measure is. And now we have to verify some more properties which we have not done so far. And one of the properties that we want to establish is the countable additivity that we shall define soon. And you recall, the outer measure has been proved to be countably subadditive. That's something that we have. Okay. We also proved that the outer measure is finitely additive. So this much we have. Okay. So we have proved two things. That is m star. This is the outer measure, is countably subadditive, and m star is finitely so this means the following. If E1, E2, etc., Ek are finitely many subsets of R such that it's a disjoint collection in the sense that Ei intersection Ej is empty whenever I is different from J. In that case, we proved this. This is what we have. So we assume finite collection of subsets of such that Ei intersection Ej empty whenever I is different from. Then we have shown that m star of is equal to sigma I equal to 1 to k star 1. This is what you call finite additivity. And of course, so many times we have said what countable subadditive is. So what we are now looking for is that for measurable sets. Now this is true for every subset of R. Now what we are going to show that for script M, that means the collection of all measurable sets, Lebesgue measurable sets, over which m star is equal to m, the Lebesgue measure. We want to prove that the countable additivity is right. So this is our Next result. So let us prove this. So theorem. Lebesgue measure is countability. So that we have already said what exactly we mean by countable additive is this. That is, if the collection EI infinity is a disjoint collection of measurable sets that means EI belongs to script M. That's the meaning. And we also have the term disjoint, and EI intersection EJ is empty for I not equal to. This is what we have assumed. Then is measurable means belongs to M, and measure of measure of E. Now this is the result that we want to. Okay, let us prove this. Now you see there are certain things which we have already proved. Okay, so recall the results namely the first one is that union 1 to infinity. That means if the countable collection EK is a measurable, then their union is also measurable. Okay, or EK belongs to M implies union K equal to 1 to K belongs to M, and you don't have the need the assumption that this is a disjoint collection for that. Second problem is outer measure M star is countably subadditive and hence M is countably subadditive. Now this happens inside script M. So inside script M star of E equal to M of, okay. So the third property is that we have proved for each N, M of equal to sigma k equal to 1 to N Ek whenever these are disjoint collection of measurable sets. The collection Ek is a disjoint collection of sets scripted. So these are the three results that we already have. So what we need now is to prove the countable additivity of the measure, and this means that we have to show that if Ek is a countable collection of disjoint sets in M, then you have sigma k equal to 1 to infinity, or M of sigma k equal to, or union k equal to 1 to infinity, k equal to, that means replace this by a countable sum. That's all. Okay, right. So in the light of 2, all that we need to M of is greater than or equal to Okay. For EK belonging to A and EI intersection J empty whenever I is different from. This is what we need to prove. So once you prove this in the light of what is called the subadditivity property, it follows that there only one side inequality we have to establish, but the other one is already, and m star is equal to m for every element of script m. Now what we have is we have the following, namely union A equal to 1 to n Ek is contained in. So we are taking all Ek in M and there is no problem that, see, the script M is closed under countable union. Therefore, this is in M. So we can write. Therefore, by monotonicity of M star, what we have is M star, which is the same as on M. We have M of K 1 to infinity Ek, because this belongs to M, so you can M star of that is equal to M. Okay, this is greater than or equal to M of K equal to 1 to n. This is and this is true for every so now you see that it shows that for each n and that is M of one to infinity K is greater than or equal to sigma n. Which implies further the LHS is independent of of n and is valid, and the above inequality is valid for and therefore which implies one to infinity. One to infinity. Plus that equal to now using now countable subadditive. So that proves the countable additivity. Okay. Now what more things are there? So let us now just recall some of the things that we have already proved and to sum up and write everything in the form of here. So we have the following. What are the properties of this that we have already seen? We have already seen that is a sigma that we have, and this is what is called the Lebesgue measurable sets. Okay. Further, measure of I equal to length of. Now this follows from the fact that I is an on so it is the length of the interval. For any interval, okay. The other property that we have is this. We have shown that m star of e plus y equal to m star of e for every e subset of. Now, if e belongs to m star is m, and hence m of e plus y for every e belonging to script m and y belonging to. So now let us sum up all these things in the form of a theorem. It's just repetitive, but nevertheless. So we have the following. A countable collection of sets, the set function Lebesgue measure defined on the sigma algebra script m assigns length as to each interval translation variant and is countable. Therefore, all the properties that are required of a Lebesgue measure are satisfied. So we have finally successfully constructed what is called the Lebesgue measure on a class of measurable sets. We still do not know whether it is valid for all arbitrary subsets of R. That we will explore soon. But at least we know, I have been repeating this quite often, that it is defined for a huge class of sets, a big desirable class of sets like open sets, closed sets, on the whole of R, on the empty set, and then all what you call all F sigmas, all G deltas. So, okay. Thus, we have successfully defined what the equation is. Okay. Now, what we do is we go further. So, we explore the second part of this title, namely continuity. So first we have to make some sense for this, what exactly by continuity. Now you recall that M is a map from a non-negative set function satisfying very nice properties. Okay, so we want to explore the continuity of this particular function. So how do you define continuity in this case? Because we call that subsets of R. So what do we mean by continuity of so we should establish or have some clarity about what norm we use to talk about continuity. So essentially, see, you are talking about a map from collection of subsets to a non-negative. It's a non-negative function defined on a collection of subsets. So what do you mean by continuity? So to assert this or to make sense of this statement, we first define what exactly you mean by convergence. So essentially, you recall whenever you want to talk about a continuous function. Okay. Now you want to talk about a continuous function. So what do you do on R? So let us say on R or on any matrix. It's continuous real valued function on a matrix. What do you do? Choose a sequence, and then whenever the sequence converges, the value, so xn converges to x, implies fxn converges to f of x. Now this is the criteria that here, what is that you have? You are now talking about M. Okay. So what do you mean by a sequence here? Okay, what sequence we are? And then it should be a converging sequence. So let us work on it. Right. So we define what is called an ascending sequence of elements in M and a descending sequence of elements. So let us define a countable collection is said to be an ascending collection if EK for every K. What does it mean? Means, you see, let me use Venn diagram because I'm not just forgetting that we are. Can be in the general scenario also. So this is what you have. So see, this is your EK, and EK plus 1 is a superset of EK. So what you have is, you have a collection of sets in the ascending order. So it's something. Etc. Okay. So this is what you call an ascending sequence or ascending collection of sets. Now we define likewise descending collection. A countable collection of sets one to infinity is said to be descending. Said to be descending if need two properties. Two properties are okay. So this is EK plus 1 that is, you have EK plus 1. So you have a scenario like this, that you have once again a sort of telescopic one. Now K and EK plus 1. So you can say that it's telescope. That's the meaning. Okay. That is, either is ascending, K is contained in K plus 1 for every K. It is descending if K plus 1 is contained in K for every. Now, this terminology is enough to talk about what is called the continuity. Because as I said in the beginning, you should have some convergence notion in the domain space. Okay? So that's what we are teaching, right? So we'll see, as you will see. Processes. The following what are they? One, suppose is an ascending collection of measurable sets. Then measure of AK a very expected result, right? So AKs are having this structure, ascending structure. So what you have is have measure of A, measure of K plus 1, so on. So measure of A. So see, take the union of all this. That's equal to limit of the sequence M. So you have two things here. One, suppose you call this A, right? Okay, I'll take the second step regarding sending collection. If EK is a descending measurable sets, that means in script M, and measure of D1 is finite. It's the largest amount. It's finite measure. Then you have got measure of intersection of this is equal to limit So what you have is this one, of course, a collection like this, and in this case, you take the union of that. See, if you take the union up to k, then it is going to be ek. Take union up to infinity, it's going to be the entire collection. And that, the measure of that is going to be the limit of the measure of. In the other case, what happens if it is descending? Then you see that we are now talking about the intersection, because it's something that converges down to something. You don't know the limit actually. Okay? What you know is it's a descending sequence. And then what you say is that take the intersection of the entire collection, okay, and take the measure of that. Important part is that is the measure of that is going to be the limit of the measure of k as k tends to infinity, because it's a decreasing sequence, whereas here you are talking about an increasing sequence. So with the ascending collection, you have a increasing sequence. With the descending collection, you have a decreasing sequence. So prove it, and proof is what? So with the ascending sequence, you have an increasing sequence of numbers. With the descending sequence, you have a decreasing sequence. Right. So let us prove the first one. First step for ascending sequence. So there exists there are two cases here. One, there exists a so we take two cases. Assume what is the consequence? The consequence is that for all k greater than k naught, m of ak is infinity. So you see, after some stage, the sequence, the number sequence that you get out of it is going to be a sequence with a tail, right? By the monotonicity of m. Right? And therefore the sequence converges to or diverges to infinity. Okay. See, it's a monotone sequence that you end up with. Okay? It's a monotonically increasing sequence. Okay? Right? And it just diverges to infinity. Now B, what happens? Right. Assume is finite for every. Now define A naught to be empty set. And now further define Ck equal to Ak minus and put a slash Ak minus 1, so it's all the same. So it's a better notation for every k greater than or. Then what you have is this. See, this is your AK, this is your AK, and this portion is what you call CK, right? The collection CK is a disjoint sets, and they belong to in what? Script. I mean, that's easy. Now you also have union k equal to 1 to AK. And this is a disjoint curve. This is a telescopic. Okay. Therefore, by countable additivity of M, we have M of which is equal to, now we are applying countable additivity here, sigma k equal to 1 to M of Ck. Therefore, let us work it. Which is equal to sigma Now let us use this. So you have AK is ascending, and ascending sequence, and therefore we can now use excision. Please. By excision property. By this is what you have. This one, and this is equal to limit k equal to this is just the usual property of series. Okay? And this, this is equal to to use this property, then you end up with okay, because you have this property of AK plus AK minus 1 contained in AK, and then you have got this M of, so that the terms get cancelled. That's all. Simple. And this is equal to, that M of A naught is empty set, therefore that is 0 equal to limit intending to of that completes. Okay, that completes. So this completes the proof of part 1 in both the cases. Now we take up, so in this case what happens? See, you get an unbounded sequence, you get a bounded sequence, but both monotonic. Okay, and therefore see it converges, and in the first situation it diverges to infinity, the second situation converges, and the limit n tending to M of A. Now we take up the second. Now in the second case it's a descending sequence. So what you do is the problem you convert into the case 1 and then how do you do that? Define bk b1 slash. So this is what we are assuming b1 has finite dimension. Okay, and then this is your bk. This is what you call okay. Now look at this collection. That's what I said. Convert the case 2 cleverly to the case 1 and then now so what you get? Share of union A equal to 1. This is equal to limit A tending to measure of T. Okay, so this is using 1. Now apply De Morgan's law. We have union k equal to 1 to infinity dk. This is equal to k equal to 1 to infinity b1 slash b2 and that by this is where you apply b1 slash union or rather intersection a equal to 1 to right, because it's a descending sequence. You are at each stage you are increasing. So this is vk plus 1 comes under this and so on. So you see that this is what the intersection becomes. Union. Effect of union becomes intersection. And therefore, you see that by excision property, what we can have is this. Of pressure you have this m of pk, which implies m of one to 1 to infinity. Okay. This is equal to limit n tending to nb1 minus okay. So we have got something for this, and this is it. Let us work that. Hence, again, by excision property, what we have is this m of this is equal to okay, and that's equal to, that is mb1 minus m of dk. This is equal to n tending to infinity of and you know that mbn what you end up with is this so that is exactly what we want. Okay, so that completes the proof of this. Okay, so with this we shall conclude today's discussion. Thank you very much.